Good morning, pre-cal students. Man, the internet's getting slower and slower. I was trying to upload my last uh, lecture recording to YouTube. And boy, I think everybody's using the internet right now at this time. It's even with my enhanced speed, I'm still struggling, I guess, as it's everybody. But that's the price of all of our technology. Now, what we want to do today is finish up our work with the trigonometry. And so what we're going to do, I would like first to do some examples using some of the identities that we developed last class, and there were a lot of them, but again, these identities just help us understand what we already know about the unit circle and trigonometry, also with the right angles that we have from the triangles. And so with that, I would like to do a couple of examples there and then talk about some basic trig equations. We've done trig equations since 6.4, and especially with the law of sines and the law of cosines. So that set the groundwork. And now what we want to do is just add a little bit more algebra that we already know and see how we can actually use some identities to solve trig equations. So let me share my screen. And let's see here, I might have to, yeah, there we go. It's living. Let me move Professor Ron over. Let's see, get the balance a little bit better here. Yeah, there we go. And let's see, a little more exposure here. Okay. So the first example that I wanted to do, we're going to use again. Let me bring this down a little bit to make this a little bit wider. There we go. Good old IP vote. So what I wanted to do was do an example that I'm actually going to use again in solving an equation, but it's that lemma that is an identity that connects the sum of sine and cosine with the sign of the addition formula. So here's an example. So we've got this. These are some that I've done during conference hours, and I thought they were good examples. So we have 3 sine of pi x minus 3 root 3 cosine pi x. So here we're seeing that the x has been replaced with pi x. So we're making the period smaller, but our lemma looks like this: a sine x plus b cosine x. And then we have the Pythagorean part, the a squared plus b squared square root, and then the sine with the addition formula, that is the sum in the argument. And then of course the tangent of phi is determined by b over a. So again, it might not all, like for instance, if you're in a class where you find this to be a solution to maybe a differential equation or something, and you need to get a quick sketch, in this form, it's really tough. And so what we're finding is that if we're trying to graph, this lemma is very useful. And then also if we're solving an equation where we need to combine 2 terms into one, kind of like solving logarithmic equations. It's the same idea. So all these techniques that we've used before, we're going to continue to use with equations. So I think it's going to make it very straightforward for you. And then of course, I'll remind you of Professor Ron's lemma. So now what we can see, a is equal to 3 and b is equal to the negative 3 times the square root of 3. And so now if you want, we can go ahead and get the tangent of phi. Tangent of phi will now be b, which is 3 root 3 divided by 3. So this gives us the negative square root of 3. So this will allow us to solve for phi. So we get inverse tangent of the negative of radical 3. But of course, this is an odd function. So we get the negative of inverse tangent of root 3. And of course, that's where the sign is √3/2. So that's going to be pi/3 with the negative. Now, when you look at this, the only thing that's left is just the a squared plus the b squared. So a squared plus b squared. That'll give us 3 squared. And then we square the -3. That'll give us 3 squared. And then, of course, if we square the square root, that just gives us 3. So that's a 9 times a 1 plus a 3, right? We have a 9 in both, times a 1 plus a 3. And that's 9 times 4, which is 36. So these numbers are really nice. We don't always get that, but that's okay. We're glad when we do. So now we get the square root of a squared plus b squared, and then we have sine. And then, of course, we replaced x with pi x. And then we have phi, which is negative pi/3. Now, of course, if this is not a nice number, we can always just replace it with the inverse tangent. That's still exact. It may not be something from the unit circle, but that certainly makes this still very powerful. The exact computation allows you to write anything regardless of the numbers being available to us on the unit circle. We're seeing that the power of the exact computation is what we want. And so now this can be reduced, and we could factor the pi here if you like. So this would be 6 sine pi x minus 1/3. So now when you look at something like this, again, if you were trying to solve an equation or graph this, you've got the k, you've got the shift to the right, you've got the vertical stretching. So this is much more usable in this form than the difference here. So again, this is a very useful identity here, very, very useful, and something that we can work with. The idea again is finding ideas that put the trig functions together in ways that make it useful for the types of problems that we have to do. Now, I have another example that I want to do before I talk about the power reducing ideas. And I think this is a good one. Remember, we have this nice interplay between the inverse trig functions and the standard trig functions, where we use the assignment for the inverse trig, and then from that we take the triangle that we get from that. You can still do that. So there are lots of examples where you'll be able to use that technique. So nothing has changed. We just have some new identities. But to get used to these, let's try this one. So say we'd like to compute the cosine of theta minus phi. Now, of course, we need some information about phi and theta, and here's what WebAssign gives us, or you can just make these up. They just have to be consistent. So we have, in this case, cosine of theta is 5/13, and theta terminates in the fourth quadrant. So the arithmetic is the same. So when we look here in the fourth quadrant, we know x is positive and y is negative. So that defines the arithmetic of the fourth quadrant. And then we're given that tangent of phi is the negative square root of 3, and that phi terminates in the second quadrant. Now, of course, what's the arithmetic of the second quadrant? We know that x is less than 0 and y is positive. Sine and cosine are more complicated than tangent and cotangent, and of course, secant and cosecant are just sine and cosine reciprocated. So we just keep track of what we need and use what we need when it gets us to the next step of the problem. Now, when we look at this, we know that we're going to have sines and cosines in the subtraction formula or the difference formula. So let's go ahead and draw the reference triangle for each of these, and then we'll have our arithmetic here. So here we can think of a reference triangle, a triangle in the first quadrant, where we have adjacent over hypotenuse. So this will be 5 and a 13. And so now we can square this. 13 squared, that's our friend, that's 169. And then of course we can square 5 and get a 25. So again, we'll get what, a 4 and a 4 and a 1. But that's again, we get a nice Pythagorean triple here. So we can assign this to be 12. Now for this one, we want to again use the reference triangle. And we'll have a phi here. And in this case, again, we're thinking of these as being like reference angles, but I'm not putting bars over them because you can remember the arithmetic from what I've written here. That makes the notation a little bit easier to follow. So we're going to think of opposite over adjacent. And so now we can square these out. Square the root 3, we get 3. And square the 1, we get 1. So 1 plus 3 is 4. And of course, that's just 2 squared. So we get a nice triangle. And we know a lot about this triangle. That's one of the ones we started with when we didn't know much. You know, of course, the shorter side is half the hypotenuse, and then the longer side is the square root of 3 times the shorter. So you understand that triangle. So now what we can do is just rewrite this. So we have cosine theta, cosine phi. And then of course with the minus, we get the plus. And then we have the sine theta and the sine phi. So like we've done before, we just have to fill in the numbers. So cosine theta is given 5 over 13. And then we need cosine of phi. Again, remember the cosine will be negative in this quadrant. So we're going to get adjacent over hypotenuse. So negative 1/2 following that. Plus, now sine of theta, back to this triangle. Remember the y is negative, so we get a negative sign. So we do opposite over hypotenuse. So this will be negative 12 over 13. And then the last one is sine of phi. Again, here in the second quadrant, the y is positive, so we get a positive number. So this will be opposite over hypotenuse. So that'll be square root of 3 over 2, which we already know. And so now we've got a common denominator of just 13 times 2. So of course that's exact, and I'm sure Webberstein probably wouldn't be too upset with that. So we get a negative 5, and then we get a minus 12 times square root 3. And if you want, you can just factor this. You don't have to, that's certainly fine. So we have 5 plus 12 square root 3 over 26. So again, these are still arithmetic problems like we've been doing. Now we just do everything. We use our arithmetic of the unit circle, we use our right triangles, we use our new identities, but everything that we do, when we look at this problem, all of this is old. The only new part is this. So all the techniques we've learned, you will continue. Don't worry that the identities look different. That doesn't change anything. The arithmetic that we do is fixed. That will never change. When you take calculus, trig is still trig. So I think a lot of students lack confidence at times when you have all the ingredients to do great work. Just believe in yourself. Now, I have an example here. Let's see. Yeah, this will be a good one. One thing that, ladies and gentlemen, that you do in calculus, in Cal 1, you look at the differentiation theory and limit theory of the transcendental functions, the exponentials, the logs, the trigonometric functions, and you do the beginning of the Riemann sums and the fundamental theorem of calculus that tells you how to compute definite integrals. Now, when you get to Cal 2, you're going to actually work with some powers of trig functions that you really could have done in Cal 1. I mean, it's just a matter of how much can you squeeze into Cal 1. They're 4-hour courses like pre-Cal. It's too much work. So you just kind of push some stuff into the second class, which is Cal 2. And so what we might be interested in would be finding an antiderivative or indefinite integral, or even possibly definite integral of a power, a positive integer power of a trig function. And so what we might want to do here is write cosine of x to the sixth power in terms of single powers of the cosine. First power, single powers of the cosine function. Now, again, when you take Cal 2, you'll also learn about integral tables, and integration by parts is a nice way to develop integral formulas to deal with powers of trig functions. And those are called reduction formulas. But right now, students have to make the choice. They're like, well, am I going to remember the reduction formula, or I'm going to use the power reducing from trig? It's just your call. So when you look at this, you're thinking, all right, well, let's just think about some things that we know from the last class. That is, we have this reduction formula. I'll use the same letters I used last time. We have cosine of a quantity squared when we use the cosine of the double angle formula. And this was 1 plus cosine 2a divided by 2. Okay, and so that's what we call the reduction formula, because we reduce the power of 2 to the single power, or the 1 power. And then if we've got something here that's the third power of a square, we would need an expansion formula, a binomial. And I'm going to write down a formula that we used the very first week of class. Again, this is a different A from this, but I used that A yesterday. So we want to use the formula of cubing the binomial, which we will review at the end of the class. And if you remember this, you might already remember this, putting this on a note card. This is A cubed plus, you can multiply this out, but the binomial theorem will give us an easier way to compute this. So this will be what? A squared B plus 3ab squared plus b cubed. So that would be, these ideas, of course, would be convenient. This is necessary. And of course, this is good to use, or you could just break this down as cosine squared times the fourth power. But this is a little bit more to the point. Now, so when we look at this, we say, okay, well, cosine to the sixth power can be written as cosine to the second power quantity to the cube. So raised to the third power using the laws of exponents, which again, we use all the time, especially with the logarithm. What's a logarithm? Power of the base. And so now we just say, okay, well, now we can take this formula and make a substitution here and get the binomial. So this will be 1 plus, so we double the argument. So we get, like here we have 2a, we get 2x cosine 2x divided by 2 raised to the third power. So in doing this, we will be well on our way to generating functions of cosine that have lower power than 6, a lot lower. So we're already en route to doing that. So first, what we're going to see is that the 1/2 is raised to the third power. That's 1/8. So we don't care about that except to move it to the outside and get it out of the way. So it's kind of in the way. So we'll just kind of use this to collect fractions that we just don't want to have to deal with inside the brackets. So now we'll apply the formula. Note, we can use A. This is just like doing the trig. That's why I'm doing it. We have A's and B's. A is equal to 1 and B is equal to cosine of the double angle. So that's the first power of cosine of 2x. So we're good to go. So let's fill it in. So we're going to cube 1. Well, we like that. That's just 1. And then we get 3 times 1 squared times b. So that's plus 3 times 1 times cosine of 2x. Ones are our friend. So here we have a 3 times a 1. So we have a 3 times the square of cosine 2x. Using our nice shorthand notation. So when we read this, we say this is cosine of 2x quantity squared, or we're just lazy and say cosine squared where the argument is in context. And so we've got that. And then the very last one is the cube of this. So we have cosine 2x quantity cubed. Now, when we look at this, this is indeed a big improvement. The 1 is fine. I mean, that is what it is. That's a first power of cosine. That's good. Now here, that's a square and that's a cube. And so we can break this down again, and we can, again, apply the reduction formula to the powers here, again, doubling the argument. So let's keep going. So we get 1/8. So we have 1 plus 3 cosine 2x. Now we're going to have a 1/2 from the square here using the power reducing. So that'll give us a 3/2. Just pull it to the left there, and that gives us what? 1 plus cosine. Now we double the argument and we get 4x. So these identities are easy, but you have to respect them. It's like respecting the arithmetic of the unit circle. If you don't respect it, the problems don't work out very well. So now we've got cosine times cosine squared, thinking of this particular deal here. Just do a little sidebar. This is just cosine of 2x. I put a little dot there for emphasis, times the square. Okay, so that's good. It's a first power, but that's not a first power, so we need to reduce that. So this will give us plus cosine 2x. And then, of course, we'll do the same thing. We'll just do what we did here, and we get a 1/2. So I'll just stick the 1/2 right here. And this gives us 1 plus cosine 4x. So again, we apply the reduction formula to this to get this factor and these guys, just like we did applying it here to get this. Now, we can easily reduce all of this, but now we've got these 1/2s, which we can just slide out and hit these with 2's to get rid of the fractions. The fractions, you know, aren't bad, but they do get in the way a little bit. So 2 times 8, that'll give us a 1/16. So we get a 2 plus a 6, hit it with a 2. Now, of course, here the 2's gone, and that leaves us with a 3 plus 3 cosine 4x. Now the 2's gone, so that leaves us with a cosine 2x plus a cosine 2x times cosine 4x. So again, just doing a little house cleaning. So we have 1/16. And now what we can do is combine like terms and see what we have. We have a 2 and a 3, which will give us a 5. And now we have 6 copies of the 2x argument and 1 here, so that gives us 7. And then what's left? We've got this term, and they're not like, so we'll just write them down. Now, this when I look at the WebAssign, this actually satisfies what they ask. But from a calculus student standpoint, you'd want to do a little bit more work, and I'll share that with you. Notice first power, first power, first power, first power, and these are different arguments. So that's cosine 2x first power or single power, and cosine 4x single power. So from the standpoint of a calculus student, these would all be easy antiderivatives. But this product here would require either the use of the formula I'm going to quote, the product to sum, to make it look like one of these guys, or the technique integration by parts. And students tend to not want to have to pull out the integration by parts with something like this, especially when you can use a trig identity to break it up into two simple pieces. So when you do your calculus, I'll say more about this, there's always a reason to break things down. Things like this are easy to integrate, but this requires more work. So I'm going to reference one of our theorems or identities from yesterday. Here we have a product of cosines. Notice we have this formula here, which we derived from the addition and subtraction formulas. So we have cosine A, excuse me, let me get the two cosines. Cosine A cosine B is 1/2 cosine of the sum plus cosine of the difference. So let's write that down. So this is something we can use. So recall, we have cosine A. Well, let me not write all the parentheses. Save a little time. Cosine A cosine B is 1/2 cosine A plus B, well, we need the parentheses, plus cosine A minus B. So if we're in a calculus class, we want to go ahead and do that. So this is going to help you the second time you see this. So now notice we can just say A is 2x, doesn't matter which order you use, if it did, it wouldn't be any good. B is 4x. And so we can fill that in. So we get 1/16. So we have 5 plus 7 cosine 2x plus 3 cosine 4x. Now we do this, the 1/2. So we have plus 1/2 A plus B, that'll be 6x. And then A minus B, that's going to be negative 2x. But of course, the cosine function is even, so it absorbs. So we just get plus 1/2 cosine 2x. And just remember, cosine of negative 2x is just cosine of 2x. So we use that right there. Now, easy, so simple. So just to make it look nice and pretty, so you're going to put this in a textbook that you're writing, and you want the publisher to think you're a professional. So we'll get rid of the 2's here. So let me just save the time and multiply the 16 by 2 and get a 32. So now 2 times 5 is 10, 14, cosine 2x, 6, cosine 4x, that's gone, plus cosine 6x, and the 1/2 is gone, plus cosine 2x. So now we can collect everything. So this would be the best possible form to do an integral. And you're thinking, boy, that's a lot of work. Well, you can apply the reduction formula, and that's a lot of work too. So you just have to kind of pick which one you prefer to do. So now we only have what? We've got the 10 here. So we've got 10, and we've got a 2x and a 2x here. So that'll give us 15 copies. So these are taken care of. And then we have the 4x and the 6x, and they are unlike. So we have 6 cosine 4x plus cosine 6x. So like I say, the WebAssign will be fine with this part, but I just want to give you the little extra work here that again, if you were doing this integral by itself, you would go straight to this identity here, product to sum, to make the integral easier. Now, of course, if you use a different technique, the antiderivatives will look different, but you're going to learn the mean value theorem in calculus, which states that functions having the same derivative differ by a constant. And that's what you'll have to believe in. Otherwise, you won't no calculus. It's kind of like you take the leap. When you're in Algebra 1, you finally decide that factoring is relevant and that it's actually real and true. If you don't, you never solve any equations. So the thing about calculus is that you're going to learn a lot of new theorems that you have to embrace, or you will come to grief. I mean, they will be required. So why is this so much better than this? Well, this, when you see this, you cringe and say, well, I don't know what to do. So I'm not going to use the reduction formula. So you're thinking, well, that's how you would integrate a square of a cosine right here directly. Those would be two easy integrals. And see, now when you look at this, you think all straightforward. And one of the integral formulas, one of the basic ones, would be that of the cosine integral, where u is a differentiable function of x. Cosine u du would just be sine u plus a positive constant. And so if you can rig it down to something this simple, these integrals are easy. So in general, even powers of trig functions are painful. Odd powers you can rig usually, and they don't take nearly as much work. But I always tell my students, you always expect this on a calculus test, at least a fourth power or possibly a sixth power, and you got to work it out. So otherwise, and so it's not just in time calculus. You learn this in pre-cal, so when you get to calculus and see it again, you're like, oh, I get it. I know what to do. So this is certainly, as I've said many times, pre-calculus. Okay, so that's a good example. Hopefully that was a fun problem. And again, using a lot of algebra techniques that we need to know. Now, what I want to do is look at an example that utilizes the half angle formula. Now, remember the tangent of the half angle was that miraculous formula that didn't have the plus or minus in it, and you will use that more in your WebAssign practice, but you will also use that in Cal 2 as the basis for the Weierstrass substitution. So what I want to do now is say, if you're just looking for a computational exercise, how we can use what we know with a little bit of the new stuff to make the problem simple. So lots of times in the WebAssign, just to get you familiar with these new identities, you'll have to do arithmetic problems. And they're not hard, but you have to follow the formatting. So the problem says that it wants the sine of the half angle, it wants the cosine of the half angle, and it wants the tangent of the half angle. Of course, like the last problem or the previous problem or the one before the last problem, we need a hypothesis. So here's what we're given. We're given that cosine of x equals negative 15 over 17. And we're given where x lives in the third quadrant. So that at least is consistent. So and it's not stated like we normally say. We'll just say like x element of 3. This is just giving the inequalities to kind of give you a leg up of how you do this. Now, of course, if we start with the sine of the half angle, we have to choose the actual arithmetic sign. So first, what we want to do is just remind ourselves of this half angle formula. So recall, we get this using the power reducing. Remember, everything's kind of moving from the cosine of the double angle. We get the power reducing in the half angle. It's a very popular function. So we get plus or minus the square root of 1. And of course, we double the angle, cosine x divided by 2. This is not a very user-friendly problem because we have to determine this. It's not like the half angle of the tangent where we don't have the plus or minus. So we're stuck with it. So now we say, okay, well, we can determine what we need here if we know where x over 2 terminates, which we can easily do from here. So the inequality makes that easier to do as opposed to just guessing. So we divide by 2. And of course, multiplication by 1, 2, that preserves this. So again, multiplication by 1/2, division by 2. So this will be 90 degrees, x over 2. And then of course that gives us what, a 1, and then a 3, and then a 5. So now we see, and that's not a surprise, x over 2 is in the second quadrant. Of course, in the second quadrant, x is negative and y is positive. Okay, so you're thinking that's terrible notation. We got x over 2. Well, let me look at it. Let me write it this way. In this case, I could do x over 2 is negative and y over 2 is positive, but let me just say it this way. Cosine is negative, sine is positive. That way we don't have a conflict with variables. But I think you knew what I meant. It's just, we want to be precise. So now when we look at this, we're thinking, okay, we're going to have to choose the positive sign here. So this means select the positive from our arithmetic here. So first, because we're lazy, let's just look at the square of everything and then do the radical. Never do radical computations. Drawing a big old radical and doing that's the biggest waste of time. I never do that. Do the square of that and then take your radical, just like you do with the quadratic formula. If you want to get better, you have to improve your techniques. And that's what I'm going to be looking for in your written work, because that's exactly what I teach you. And this is not for amusement. This is to make you better. This will make you better if you follow the ideas that I try to put forth and come up with your own signature. So now what do we need? We need 1 minus, well, cosine is what? Negative 15 over 17 divided by 2. Well, okay, so that's plus minus minus, so that's a plus, but we need a common denominator. So we have a 17 times a 2. So this gives us a 17 plus a 15. Addition is really odd how it works out. The thing is that neither of these numbers is divisible by 2, but since they're both odd, their sum is. So number theory tells us what to do. Number theory kind of drives everything we do. So this is a 32, 17 times 2. And of course, 2 divides 32 16 times. So that makes the arithmetic trivial. So now we're thinking, or we go over here where the sign for this particular input, we've got a positive sign. So this implies that sine of x over 2 will now be the square root of that, which is 4 over the square root of 17. So that was the easiest way to get sine of the half angle. Again, do all the arithmetic that we do beforehand. None of that has changed. So now when we look and say, okay, well, we can just use the fundamental identity to get the cosine, but remember the cosine is going to be less than 0. So let's look at the square. So cosine squared of x over 2 will be 1 minus the sine squared of x over 2. So there's the square right there. So this is 1 minus 16 over 17. Again, look at the square and then apply the square root. That way your calculations are easy. And so that's just going to be a 17 minus 16. So we have 17 minus 16 over 17, which is just 1 over 17. So this implies, with the arithmetic of the second quadrant, that we select the negative. So cosine of x over 2 will be the negative 1 over square root of 17. So again, to get the ball rolling, it's like doing the triangles. Maybe we have to start with the law of cosines to get the process moving, but then we can, use the law of sines. We do that all the time. It's standard fare. So this is what gets everything rolling here. But now we're done with these half angle formulas. To use them now would be a waste of time. So we just say, well, tangent sine over cosine. So tangent of x over 2. And the sine is determined by the sine and the cosine, so we don't have to worry about anything. So we've got, in this case, sine that's up here, 4 root 17. And then we divide by the reciprocal of this, or excuse me, multiply by the reciprocal. We divide by this, so reciprocate and multiply. So this will be the square root of 17 over -1. And the 17 radicals absorb, and we just get -4. Of course, that makes sense here because the cosine's negative and the sine is positive, but we get that automatically. We don't have to select it. So now what we can see is that nothing about this problem is new except that. And that's really not new. We actually already knew it. We just didn't write it down yet. And it's certainly no more difficult than anything else we've used. All the arithmetic is the same. So you don't, just because you get a new identity doesn't mean you turn your brain off. So just be careful when you work with these problems that you also bring to the table everything you already know. And it doesn't mean that, oh, well, if I use this, that'll make it wrong. No, if it's a legitimate procedure mathematically and it's useful, then use it. And as you work the problem, a lot of times in conference hours, I'll start a problem the way the student had started on it, but I'll say, you know, you could do this, or the student will say, well, I want to use this first. I'll say, okay, if we use that, then we're going to have to do this. So again, be true to yourself, stick to your game plan, unless it just, you know, puts you in a ditch and you have to start over. But usually if you studied and you thought about what you're doing momentarily, you know, 15, 20 seconds, you should be able to come up with an answer. Okay, so now, again, remember everything we've done. Don't leave anything at the door, so to speak. Let's look at some basic equations. Now, when it comes to trig equations, we've already been solving them, but I want to remind you of Professor Ron's lemma. So 7.4 and 7.5, and all the instructions are this way in WebAssign. They'll say if it's not a trig value you know, then approximate to 2 decimals. But if it's something you know, it's unit circle, then you write an exact answer. So there are no instructions to ever approximate unless you like end up with sine of 1.5 radians. But then of course you could just write that as sine of 1.5, which is exact. But in that case, WebAssign would say, okay, I want you to get some practice using a calculus approximation with the Google calculator. So my understanding is that if WebAssign asks for an approximation in those cases, it will be looking for that. However, when an exact computation is needed, WebAssign is very flexible, very flexible. So as long as it's exact and you didn't, you know, use some crazy mathematics, you'll get that green check. So with the trig equations, we just have to remember that sine and cosine, and then therefore secant and cosecant, are not one-to-one on the unit circle. Cotangent and tangent have a period of pi, and they're one-to-one on that. So when you solve cotangent or tangent equations, you don't need Professor Ron's lemma, because they're one-to-one on their principal period. Then you just tack on pi times k, or if the period changes, whatever that is, times k. Now for the sine and cosine, they have standard period 2 pi. And so we have to remember to exhaust all of the solutions in that interval. And that requires Professor Ron's lemma. So let's remind ourselves of that. So if we have sine, we'll just take x to be the argument equals b as a legitimate equation. So we'll say we have a solution theta, in this case, And of course, I'll just X or whatever you want to call it. You can call that theta or phi or whatever. I'm just going to call a solution theta lives in the upper arc. And we're talking about away from the axes. The axes are easy. That, you know, you either get 1 or 0 when you're on the axis. So who cares? That doesn't require anything. So if this is a solution, then this implies the second solution. The second solution is pi minus theta, or 180 degrees minus theta if you're in degrees. Now, the second part of Professor Ron's lemma is that maybe you have a solution, and we've done this, and I've ranted about it forever. If we have a solution in the lower arc, then this implies the second solution, and I proved this in class, will be 3 pi minus theta. That is, if you're in quadrant 3 or 4, if this is in 3, that'll be in 4. If this is in 2, that'll be in 1. You exhaust the quadrant, so to speak. If this is the case, you can find the next one. And if it's not a nice number, you can write it exactly, okay, with the inverse trig functions. Now, the cosine, no problem. Sine is kind of a troublesome, but cosine is easy. So if we have a solution, we don't even have to look at upper and lower arc because the cosine function is even. If we have a solution theta in 0 to 2 pi, again, cosine is not 1 to 1 here, then we can get the second solution just by subtracting the first solution from 2 pi. So these are the rules for finding the second solution with sine and cosine, or secant and cosecant. So again, these also apply to secant and cosecant for equations that make sense. So again, they also have the standard period 2 pi. Tangent, cotangent are our friends. They don't present any problem to us, very easy. So that's just a reminder of where we've been. So now let's look at some examples. So let's look at 2 sine theta plus 1 equals 0. Just some simple equations to get the ball rolling. Now, WebAssign usually will say solve, and they'll say all solutions. So we want all real solutions. So when they say solve, that means all solutions. They may restrict to 0 to pi or 0 to 2 pi. If they do that, then you have less work to do, but not really. Because finding all solutions means you did the work to get the ones in 0 to 2 pi, and then you extend them just by adding multiples of 2 pi or multiples of the argument, integer multiples, that is. So maybe it's not a lot less work. So it's just, it is what it is. But when they say solve, and they may say this or not, that means all solutions. So they want you to use K for the letter for the integer, for the arbitrary integer. So when you use this, don't put an N, don't put a P, don't put a C, use a K, and use a lowercase. That's important. So now you're thinking, well, this is easy, let's just factor it. So factor the 2. So now when you look at this, this is just 0 product. Of course, 2 is never 0, so you can wish that away. But that means that the sine theta plus 1/2 would have to be 0. So by 0 product, this means sine theta equals negative 1/2. Now, when you look at that, you're thinking, okay, well, this is going to be in the 4th quadrant because that's negative. So you know that the inverse sine, it starts negative pi over 2 up to 0, then to positive pi over 2. So that's in the 4th and the 1st quadrant. So just remind yourself, where does the inverse sine live? So this is what we did with the law of sines. Law of sines is easy to prove, but it's tricky. And then the law of cosines is just harder because you got so many variables running around. And to do the exact computation, you have to be very careful. So now you're thinking, okay, well, how do I do this, Professor Ron? Well, let's just get the ball rolling. So we'll have theta is inverse sine of -1/2, but of course, inverse sine is odd. Oh, I hope it's not even. So we get negative inverse sine of 1/2. So now, of course, this is where the cosine is bigger. So this is going to be a -π/6. Π/6 in the first quadrant made negative. Now, in order to apply Professor Ron's lemma, we have to mod out by 2π because this is not in one of these categories here. So first we want to say mod out. So this will be congruent to -π/6 plus 2π. But of course, that would be a 12π minus π with the common denominator, and that's 11π/6. Now that's where we want it to be. Of course, this is in the fourth quadrant. This is in the lower arc right here, okay? So we can call the other solution alpha if you want. So then alpha will just be 3π minus 11π/6. That's going to give us something in the third quadrant. So that's going to be an 18π minus 11π/6, and that gives us 7π/6. So again, when the numbers are familiar to us, we get familiar numbers. But if they're not familiar, we still want to be able to write down the exact solution. So that's why this lemma here that I've devised is really important. You can't draw a picture of it. That's not going to work. That's great for triangles, but for this, not so much. So when you look at this and you look at this, you're thinking, okay, well, those are the solutions in 0 to 2π, and they're all in the lower arc. And now to get all solutions, we just add integer multiples of 2π. Now, sometimes when I write these in the Smart Pen videos, I'll do union symbols, but to lessen the notation and to kind of mimic what they do in WebAssign, you'll have a box. It won't have the curly braces, but they'll say separate by commas. So you can say 7π/6 plus 2πk, comma, 11π/6 plus 2πk. Now, sometimes we'll consolidate these, especially when they differ by convenient multiples of pi, but when they don't, we don't care about it. This is not redundant. All of these are incongruent mod 2π, so they're good. So this is really what goes in the box. The k for the integer multiple, and then the comma. So this is what you need to be typing. So don't be sending me messages because you put in a bunch of decimals for these. Shame on you if you do that. You know better. These are unit circle. I get so tired of seeing all these decimals, ladies and gentlemen. I do not teach you that way. We approximate when we get to the end of the problem. So please be careful with that. And I know it's not always your fault. You know, I'm trying to teach you how to do real math and not just be tethered to a calculator. So please be careful with that. I do want you to get better. And all of you are improving. Usually students miss me when they're in another class and they miss the fact that I'm very meticulous about my work. It's not something that you'll always see with every math professor because everybody's different. But usually the students miss me after they're out of my class, which is kind of backwards, but I'll take what I can get. Okay, so now a little bit of humor there. It's like, oh, that class was misery, but I guess I learned what I needed for calculus. And so then 2 years later, they come by my office and say, well, thank you, Professor Rana. I didn't like you at the time, but now you're my hero. I said, well, I appreciate it. That's good. Now that they're an engineer and making their 6 figures, I guess they're happy. So we have 4 cosine squared minus 4 cosine theta plus 1 equals 0. Now, again, this just says solve. So when it says solve, that means all solutions. Now, what I wanted to mention is that just like with the logs and the exponents, we use algebra. And so when you look at this, you're thinking that looks like a perfect square, or we could just use Professor Ron's AC lemma. But notice this is just 2 cosine theta squared minus 2 times 1 times, well, I guess that'll be another 2 cosine theta plus a 1 squared. So that has this form that we remember from the first day, even though if you don't remember this, the AC lemma works fine. I mentioned that in like the first or second week. But we have what? A squared, this is just the binomial, 2ab plus b squared equals a minus b quantity squared. And that's what we have here. This is a perfect square. So we see that the a is 2 cosine theta and the b is 1. So we can apply the theorem, the identity. So this is just 2 cosine theta minus 1 quantity squared equals 0. Now, of course, if you didn't see that, and that it doesn't matter, AC lemma will still work. You can notice if you did AC, this will be 4 times a 1, which you can just write as the product of -2 and -2, and that'll give you the -4 there. So this will do the same. I think either method is fine. You have to notice one or the other, but the AC method will always work, especially if they're rational zeros. We know that to be the truth. The theorem goes both ways. So now, when you look at this, and let me just remind you, when it says solve all solutions. So when we look at this, it's like, well, we've got the repeated root, so to speak. So this is only true if 2 cosine theta equals 1. And I'm solving this a little bit different way. Normally I just factor the 2, but now I'll just solve it like you do in Algebra 1. So this just says cosine theta equals 1/2, if you want to look at it that way. Before I just factored the 2, but you can look at it this way if you like. And so now, again, we know that the inverse cosine lives between 0 and pi. So since this is positive, we know that this will be between 0 and pi over 2, necessarily. So we have theta equals inverse cosine of 1/2. Well, that's fine. That's just in the 60-degree angle, so to speak, as we move along the unit circle to pi over 2, and that just gives us pi over 3. So when you look at this particular problem, it reminds you of the previous one, but in order to get to the solution, at least here, we had to use just basic algebra. So now by Professor Ron's lemma, this is in the arc 0 to 2 pi, so we can get the second solution, alpha, by just subtracting this from 2 pi. So the Professor Ron's lemma for the cosine is easy. So that'd be 6 minus pi. So that's 5 pi divided by 3. So now for all solutions, we have this one and this one, which are the only ones in 0 to 2 pi, and we add the multiples of 2 pi or 2 pi k. So the solution sets, think of this as the Webb-assigned box, will be pi over 3 plus 2 pi k, and then we get 5 pi over 3 plus 2 pi k. Now again, these don't differ by a convenient multiple of pi, so these are all mutually incongruent mod 2 pi. That's what we want to do. Sometimes we'll get bunches of solutions, you know, and then we start to write them down and we see that we get overlap, and so it doesn't make it wrong, it's just overkill. So sometimes we'll notice that we have some overlap and we can try to consolidate things. It just makes the solution look a little bit cleaner. Now, I want to, again, we see that sometimes when we solve trig equations that we just basically use the algebra that we've been using. Now, sometimes there might be a case where we actually get to use a trigonometric formula that's not maybe as used. So for instance, here's an example where maybe we can use one of the theorems or identities that we proved last class. So now you can see why these are useful. The first time I derived them, it seems like a whole lot of difficulty, but they're not. It's just they're new. They look new, and so they seem difficult, but they're not. So we want all solutions if we want to solve, all real solutions. So here's the example. Sine theta plus sine of 3 theta. Now, of course, if you stare at these long enough, you can solve them in your head. Okay, you can look at this and say, well, I can solve this. You can try different answers, but the thing about the procedures we show is that they help us to uncover all of the solutions. So if the problem requests all solutions, you need to be a little bit more organized. But now you're thinking, when we do the integrals, we want to take the products into sums. So this would be easy to integrate. But if we're solving an equation, we don't like sums. We like products because we like the zero product. That's the easy thing because of the nature of the real numbers. So we can look at this sum and just say, let's just use the sum to product here. Okay, so let's write this down. So recall that we have sine alpha plus sine beta. And of course, you can use, WebAssign will always give you hints, but you can use any approach you want. It doesn't matter. There's no one way to do any problem when it comes to trig equations. So you feel free to exercise whatever knowledge base you have, as long as it's legal. So having the formula sheet from the Blackboard that you have access to, or you make your own formula sheets, that's fine. Like I say, I have students that still have this, and on the back, they have all of their trig identities. And they carry this around like it's, you know, their personal identification. So you could always print out one of these if it's kind of tattered and just put all the nice identities on the back. I think that's funny. I told you that the students were looking for it on the internet. Now, of course, I'm sure if you go to Course Hero, where you see half my stuff that's been bootlegged, you can probably find that, but you won't find the code because that is not on the internet. So if somebody wants to change that, they won't be able to. Now notice here, if we look at this, we can use alpha equals theta and beta equals 3 theta. So that would be the way that we would move from this formula here to here. So let's just go ahead and say, let's get the product. So if and only if we have 2 sine, and so we have theta plus 3 theta, I'll just write it out, divided by 2. You can do this in your head, but it's good to write it out. And then cosine theta minus 3 theta. Again, we're going to get a negative that will just absorb. Now, of course, when you look at this, and this is one, I'm going to kind of throw this one out here. I was going to do another one first, so this is throwing out one a little bit earlier than I wanted to, but good challenge is always good. So now notice here that this will just be 4 theta divided by 2. So that's 2 theta, and we can divide by 2. The 2's gone. So this is sine of 2 theta. And this, of course, will be negative 2 theta divided by 2. So this is cosine of negative theta. So now we just get sine of 2 theta times cosine of theta equals 0. Now this is like so simple. And even though I've got a multiple argument here, it's not going to make any difference. And no, you don't want to write this as 2 sine theta cosine theta with the sine of the double angle. I'll show you how to treat this 2 theta here. This is easy. And what's nice about this problem is because you've got that 0 there, this makes this super simple. So we've got sine of 2 theta equals 0. This is quadrantal, so to speak. This is on the axes. And then, or cosine theta equals 0. So we don't have to even work hard here at all. So notice, we know sine is 0 when we're on the x-axis. We're either here or here. We're just multiples of pi. Pi times k. 0 times pi, 1 times pi, 2 times pi, 3 times pi, negative 3 times pi, just multiples of pi. So we solve this easily. So 2 pi, or 2 theta, equals just multiples of pi. And then solve for theta by dividing by 2. So that's just multiples of pi. Now what about cosine? Well, cosine is 0 on the y-axis. Odd multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, back and forth. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2. Odd multiples. So in this case, we say theta equals pi over 2 times 2k plus 1. Well, this is all multiples of pi over 2, and this is just the odd. So if we put them all together, we just get multiples of pi over 2. So we consolidate. So this is just the easiest equation ever. So, and then you look at this and say, oh, I could have figured that out, Professor Ron. You know, sine of pi over 2 plus sine of 3 pi over 2, that's 1 plus negative 1 equals 0. So if you thought that when I wrote it down, then that was it. But we just had to make sure we got everything. So this kind of opens the door, ladies and gentlemen, to a technique called the multiple angle. You know that this is just cut the period from 2 pi to pi. That's no big deal. You already know how to do that. So it shrinks things, it compresses things. So how do we deal with it? Well, one way to deal with the multiple angle is to treat it just like it's a plain old theta, and then extend everything, and then solve for theta by dividing at the very end. That way you preserve all the arithmetic and you get the new values, just like we were doing function transformations. It's the same thing, it's all connected. So here, this is where we get the pi over 2k from this upon division by 2. And since this is just the odd multiples and this is all, this will cover every one of them. So that's a nice problem. Know how to do this. That's a good example. Easy, but very important. Nice physics problem. Now, again, sometimes when you change up order, you give your students a new challenge. So let's just take the idea I introduced and put it into example that seems more user friendly, but then would again make you think about, how do I deal with this? So in this example, we want to solve. That's an open-ended declarative, isn't it? Solve. What does that mean? Solve. Well, if you're in a math class, it can mean a whole lot of work. You know, integrate, optimize, determine convergence or lack of it. You know, it's like solve. Such a general word. So we have tangent of 2 theta minus 1 equals 0. Okay, let me check that. Well, there we go. It did it automatically. I was gonna check the focus, but it's good. I can't click outside the box because you know what happens. I lose the IPEVO, so I've got to be careful of that. Sometimes I hit the mouse and everything goes away. So now when you look at this, let's treat this just like we did the previous problem. I mean, the tangent, that's a nice function. We know we've cut the period by 2. So the period, if we had to graph this, the period of this function is just pi over 2. So what does this mean? Okay, well, simple enough. This would just say that tangent 2 theta must equal 1. So now we have 2 theta equals the inverse tangent of 1. So, like I say, the techniques I'm showing you will apply to any equation. And depending on what you have in the equation, you can dress it up any way you like. Now, if you multiply by certain functions, then you have to make sure that you don't develop extraneous solutions. That sometimes happens. That's okay. You just have to make sure you're not putting in values that really don't solve the original. So always be careful of that if you do something more extravagant. So now we're thinking inverse tangent of 1, that's our friend, that's pi over 4. Now, of course, we don't have Professor Ron's lemma because tangent is 1-to-1 on its standard period. So now we can say, all right, how do we deal with this 2 theta? So we extend. So extend. So we have 2 theta can now be pi over 4 plus any multiple of pi. So we extend this like this is just a one variable, just like a x or something. And then if you do it this way, then you can get the necessary arithmetic upon division. Then what are the actual values of theta? Divide by 2. Theta will now be pi over 8 plus now we get the correct period, pi over 2k. That's the period of this function here. And so now we see that when we wait after we extend to divide, we get the proper period here. So you're thinking, I could go ahead and divide here and get pi over 8 and then add multiples of the new period. But students never seem to get that right. They'll divide and then they'll say pi k here, which is wrong, okay? You're leaving out pi over 2 multiples. So the pi multiples won't cover all the pi over 2 multiples, especially when they're what? Odd. So if you do pi k here, that's wrong. So in order to keep students from just floundering here, I just say go ahead and extend, then divide. That might be an easier way of keeping up with the new period. Your call though. So now when we write our solution set, we say pi over 8 plus pi over 2k. I know I sound like a broken record because all of this is the same. We just keep doing the same ideas over and over. And if we forsake one of the ideas, then we don't get where we want to go. So just remember the arithmetic of the unit circle, how we use that to define all of these functions and draw their principal graphs is all tied into the unit circle and its arithmetic, and that will never change. It doesn't change in calculus, it doesn't change in physics and computer science and finance or whatever you're doing. Surveying. We need to have a school of surveying. That would be great. If you know trig, you'd be a pretty good surveyor. So let's look at another one. I was thinking at one time Sanjak had like a surveying certification, but I don't think they do. You know, there's so much construction around that there must be schools of surveying somewhere. That's because you see a lot of them out in the field doing their work. Now, let's look at this. So we want to, in this particular problem, I'm going to extend this to all solutions, but WebAssign, I think, said solve in this interval. So it's kind of like, well, we have to do this anyway. If it's got sines and cosines or secants and cosecants, we have to do this anyway. Now, what I'm going to do is put in an example where we have two kinds of trig functions. And so this is when we might have to say, okay, we want to write this in one trig function. Maybe we want to use that lemma, that special lemma to combine the sine and cosine into the sine. Maybe we want to use an identity, which will replace the cosine with some powers of sine. So you have at your fingertips, basically, all these identities that you can use to transform an equation so it looks algebraic in one function. And that's what we've been doing since college algebra. So that's not new. So when you look at this, you're thinking, well, we can go over to the double angle of the cosine. So recall cosine 2 theta. We had lots of forms of it. We had cosine squared theta minus sine squared. And then the one that we want to use is where we replace the cosine squared with 1 minus sine squared. So we get 1 minus 2 sine squared theta. And this is good for our problem, because now we'll have an equation in terms of sine only. So we can use this replacement for the double angle of the cosine. So now, if and only if, we have 2 sine squared theta equals 2, now we'll do it, plus 1 minus 2 sine squared theta. Now, again, these problems are solved using the consequences of the unit circle and algebra, identities, whatever. So you know that you're on the right track when now you have an equation in one trig function, okay? Or you have a product, and it doesn't matter if you've got several trig functions, like on the last problem. But if you've got a product, you're fine. But this right here is no good. So this is much better. So now let's just combine everything. This will be equivalent to, well, let's just add this term to this term. That gives us 4 copies of sine squared theta equals 3. Now, of course, we can put everything on one side and factor. So we get 4 sine squared theta minus 3 equals 0. Now, of course, this is a difference of 2 squares if we could just kind of model it that way. So first, what we want to do is divide everything through by 4 to get a leading coefficient of 1, since we kind of like that. So this will be sine squared theta minus 3/4 equals 0. So now we can think of this as a square root deal to have the difference of squares. So that's where we're using our algebra again. So we have sine theta. So we don't have multiple angles here, but we know how to deal with them, and we got rid of it here by using that identity. So there you have it. So this will be minus square root 3 over 2. That is the square root of this, and then sine theta plus square root 3 over 2. This equals 0. So now when we think about what we're doing here, this is exactly what you're going to be doing in calculus. We've been doing this in algebra and pre-cal all along, but the idea is that this is like an x minus a number times an x plus a number. And so zero product says solve this. So zero product, we have sine theta equals root 3 over 2, or sine theta equals negative root 3 over 2. So again, we're back to Professor Ron's lemma. Here, if we apply the inverse sign, this is a positive number, so that means we're going to be in 0 to pi over 2 in quadrant 1. So now we have theta. If you know the inverse trig functions, you know how to do trig. I mean, it's the name of the game. If you know your inverse trig functions, you're on the next level. So now this says, okay, well, when do we get the root 3 over 2? That's at pi over 3. And now this is in the upper arc, so to speak. So we'll get the other solution by saying pi minus pi over 3, which is 2 pi over 3. So upper arc solution, which we expect. And then we'll extend this to all solutions just for an extra task, which it will be easy. And so now here we have theta equals inverse sine of negative root 3 over 2. Of course, this is an odd function, so we get negative inverse sine of root 3 over 2. Well, we know what that is. That's pi over 3 with a negative. Just know the first quadrant. If you know the first quadrant, you know everything. I mean, I know some of you have the unit circle memorized probably. But fine, good. I mean, I know it. I don't think about it though that way. I think about it arithmetically. So how you choose to process things is up to you. You do what works for you. But now, of course, this is not in the right realm. So let's mod out by 2 pi. Wrong realm. It's not in the positive realm, right? So again, this will be a 6 minus a pi with the common denominator. So this gives us 5 pi over 3. Again, this is in the lower arc. This is in quadrant 4. This is the lower arc. So now this says that alpha, the other solution, will be 3 pi minus 5 pi over 3. But of course, that's going to be a 9. So common denominator, so a 9 minus a 5 will be a 4 pi over 3. So now, modulo 2 pi, we have 4 incongruent solutions. None of these are equivalent. So we've got 4 solutions here. So this is where the Professor Ron's lemma is imperative. Without it, you miss the solutions. And again, if you can do this, then it doesn't matter if these are nice numbers or not so nice numbers. You can write down the solutions exactly. And you think, is this something you've just done all along? No, I've always done this when I've taught. Even in grad school, I'd have papers like, why are you doing this by hand? I said, because I'm a math grad student. That's why. Then they left me alone. They said, well, that's really impressive. I'm like, well, isn't that what we're here for? So the idea is that regardless of how this comes out, you can always write down an exact solution. So if we're looking here, then we can say, okay, let's just list them. Pi over 3, 2 pi over 3, 4 pi over 3, and then 5 pi over 3. Now, one thing that I wanted to make a comment here is, like I said before, when you got all these solutions, when you got these quadratic equations, notice that these two differ by pi. The difference between here is a multiple of pi. They differ by pi. Same thing here, 3 pi over 3, differ by pi. So if we were looking for all solutions, if we tacked on 2 pi k to each of these, there would be redundancy. So this is what I was talking about before, especially in the problem where we got pi over 2 times k. We wouldn't have to say pi over 2 times k, comma, pi over 2 times an odd integer, because all the integers contain the odd integers, obviously. So we could write that down, but it would be redundant. And then WebAssign would probably look at it and start to, blow smoke or something, to be like, I don't get this. There's too much there, So the redundancy may or may not always be liked by the computer algebra system. They may scan it and say, oh, those are solutions, and give a pass on it. But again, the redundancy, I can look at it this way. If you have some redundancy and it's correct, the computer algebra system may just say, okay, that's extra stuff, and give you a pass on it. It's kind of like writing the solution as the square root of 2 plus 1 minus 1. That's still square root of 2. WebAssign would not have an issue with that. So they may be okay with that. But if you're doing a presentation, you want to cut down on the redundancy. So now what we can say for all solutions is that we have pi over 3 plus pi k, because that would cover that and herever after, so to speak, and then 2 pi over 3 plus pi k, because that would cover that and herever after. So we could say all the solutions to cut down on redundancy would be pi over 3 plus pi k, and then 2 pi over 3 plus pi k. So that would be a way to write all the solutions, observing the fact that these mutually incongruent solutions differ by pi, okay? You can always come up with patterns and all but the main pattern is Professor Ron's lemma. That's what kind of connects the equations in 0 to 2 pi in the unit circle for sine, cosine, secant, and cosecant. Okay, so now that's a good example. Now what I want to do is look at some examples that cover, I want to do the lemma again, but before I do the lemma, I want to talk about another equation that may remind you of something that we did back in college algebra review. So in this case, I want you to solve. I want all solutions. So here, look at this and see if this reminds you of something you've seen before. We have 3 tangent cubed theta minus 3 tangent squared theta minus tangent theta plus a 1. Now, this, when you look at this equation, you're thinking, well, that's good. It's all in terms of tangent. It's cubic degree and tangent. And we're like, okay, that's good. It basically looks like just the polynomials that we dealt with rational zeros theorem, Descartes rule of signs, all of that stuff, Bound's theorem, things where we did synthetic division. But just like when I was talking to you about that, we always look for simple patterns. And the easiest pattern is to note that when you look at the coefficients here, that is, when you add -3 and 3 and 1 and -1, you get 0. So that would say if you replace tangent theta with 1, then you get a solution. Well, that makes sense because tangent theta equals 1 when theta is pi over 4. So you can look at this and say, well, I know a solution, Professor Ron, is pi over 4 plus pi k. Okay, and then I'll be like, you're right, you're exactly right. Because I mean, that doesn't take a lot. It's kind of like saying sine of theta plus sine of 3 theta equals 0. If you stare at it long enough, you can figure out that some multiples of pi over 2 will give you that. Okay, that's good. That's intuition. So when we observe that, we're thinking, can we get a reduced equation? Absolutely. Let's just use synthetic. So here, we'll just write these 3, -3, -1, and a 1. And then, of course, we figure that we've got a 1 here because we're just basically replacing tangent theta with x. So you can actually think of this as a polynomial in x. So we think of x equal tangent theta, so to speak. We're thinking of that to bring this back to the level of polynomials, which we've been doing all along, but we haven't used this theorem yet. We factored in different ways. So now bring the 3 down. 3 times the 1 is 3 plus the -3 is 0. And then, of course, 0 plus -1 is -1. And then -1 plus 1 is 0. Okay, well, we expected that, right? So now what does this give us? So now if 1 is a 0, then x minus 1 is a factor, or tangent theta minus 1 is a factor, right? And what's the reduced equation? 3 tangent squared minus 1. So 3x squared minus 1. So same technique that we've used. So you could take, well, and here's the thing, you can make up your own problems here. You can come up with some nice polynomials and rig it so that you can do problems like this. This is how these are constructed. Lots of times what happens is that a problem is submitted, and then through algorithmic generation and random numbers, you can actually generate other problems, which you see in your WebAssign assignments. But you have to be careful that they actually work, because when they stop working, it's like, okay, you get really crazy numbers. So now this is good. But when we look at this, we have to factor this. So let's go ahead and divide by 3. So right now, just factor the 3. So we get tangent squared theta minus 1/3 equals 0. And then, of course, you can divide by 3, and that's gone. That doesn't matter. So now this is a difference of 2 squares. So if and only if tangent theta minus 1, and then we get tangent theta minus 1 over the square root of 3, and then tangent theta plus 1 over the square root of 3. And this is what we do when we solve equations, and this is what you'll continue to do in calculus. Okay, so now zero product. So the idea here is that we take the simple equation from theory of equations, operation of synthetic division, to create a fully factored polynomial in tangent, and now zero product. So we have tangent theta equals 1, or tangent theta equals 1 over root 3, or tangent theta equals negative 1 over root 3. Now, of course, on the principal period, the inverse tangent, or the tangent, is 1 to 1. So we don't have to worry about, again, about the lemma. So just remember, the inverse tangent of x lives here, negative pi over 2 to pi over 2. So now we can move all this forward. We know what this is. This is theta equals inverse tangent of 1. So theta is equal to pi over 4. We already knew that. Now theta is equal to the inverse tangent of 1 over root 3. Now, of course, this is where we have the 1/2 upstairs and the sine of 1/2 upstairs, and then the root 3 over 2 downstairs for the cosine. So this is pi over 6. So just think of the unit circle and the ratio. And now here, theta equals the inverse tangent of negative 1 over root 3. Again, just using the unit circle. So this is the negative odd function, inverse tangent, 1 over root 3. So again, that'll just be the negative of this, or negative pi over 6. So I've made a huge point with this class, especially in everything we've done in the trigonometry, to keep all of the usage that we do consistent. So every time we do something, it just, again, reminds us of what we've already done. So now you're thinking, okay, we don't need Professor Ron's lemma. We've got 1 to 1 on the principal branch. So all we have to do is add pi k, because these are all single arguments, no multiple angle. We don't have 2 theta or 3 theta or whatever. So this gives us pi over 4 plus pi k, comma, pi over 6 plus pi k. Again, we can use this shorthand notation without the union symbols, just to remind you of your Weber sign. And then, of course, here, if you want, you can go ahead and mod out by pi to make it look better, but there's nothing wrong with this. So this would be pi minus pi over 6, just mod out by the pi principal period, and this will be 5 pi over 6. You don't have to, but it looks better. Weber sign would not bark at it. It wouldn't matter. You could put any number here as long as it's congruent mod pi. It wouldn't matter. Add or subtract any multiple of pi to this, and plus pi k, and it's fine. So now again, when we look at this, for instance, these would be the solutions in 0 to pi. So if the problem said solve in 0 to pi, you'd have pi over 4, pi over 6, and 5 pi over 6. They're all mutually incongruent mod pi. So that would be like the previous problem. So if we wanted, we can say in 0 to pi, we have, just listing, we just have pi over 4, pi over 6, and 5 pi over 6. Now, of course, if they ask you to list it in the multiple arguments, if they ask you to list them, just get common denominators and start writing them out until you get to a number that's bigger than, say, pi or 2 pi, and then you stop. So they just want you to have practice generating some of these. And of course, here, if you wanted to do that, you could just write pi as 6 pi over 6 to get a common denominator and a nice way to write them out. So again, that would be the trick if you're asked to list. Just do like we did with the transformations. Absolutely no difference. Again, it's all a level of confidence. The more you do the math, the more confident you're going to be. I often ask students in conference hours, I said, you don't mean that, do you? They said, well, no, I'm just not sure. I said, well, be sure. They're like, well, I've worked it out, but then I stopped. I said, don't stop. Just keep going. Again, the more you practice, the more you're going to build your confidence level. You know, it's like someone said, well, I had cosecant squared times sine squared. I thought it was 1, but I was afraid. I'm like, well, it is 1. I said, don't be afraid of it. Just write it out. Just move it forward. So don't be afraid of the mathematics. Let the mathematics guide you, but don't let it control you. You know, you keep your confidence level up. Now, I wanted to try this one again because it utilizes the lemma. You know how to deal with the multiple arguments by extending and then divide by that coefficient. But I think what's nice is that when you can see a problem where we multiply by a particular function to simplify it, and then use an identity to move the problem forward. So I thought this would be a good example for that. So we have tangent, in this case, theta plus 1 equals secant theta. Now, again, you can stand here and stare at an equation and figure out solutions, and that's good, because at least if you do that, then your work needs to support that. If you figure out this is a solution, so whatever I get, it better be in it, okay? That's really good. Lots of times you're doing a physics problem and you're like, well, I know this is going to be part of the solution. So whatever you get as a general solution, it better be contained in it. Now, if you look at this, you're thinking, well, woe is me, because you're thinking, well, what if I square everything? Then I could use the Pythagorean identity, 1 plus tangent squared equals secant squared, or write everything in secant or tangent or whatever. But that's kind of busy. What I've noticed about this equation is that if you multiply by cosine, you can convert that into a 1, convert that to cosine, and then absorb the cosine here to get a sine. Now, why is that good? Well, it's simple, and then we can use the lemma. So here's one strategy. Squaring is fine, but if it makes it real busy, too much work. So multiply, but of course we always have to look for extraneous. Multiply by, in this case, cosine theta. Here's one strategy to do this. So we'll have tangent theta times cosine theta plus cosine theta equals secant theta times cosine theta. Now, of course, the cosine absorbs the cosine downstairs in the tangent, so this gives us sine theta. And then when we look at it, well, cosine is just cosine. And then, of course, these are reciprocals, right? And that's 1. So when it comes to this, you're thinking, okay, well, let me, I've got all these papers here. Let's see if I can find it from the beginning. Oh, right here. Right here, right? There's our lemma. So we got this. I just want to remind you what we've done. So I'll write it again, but we've done this many times before. So again, a sine x plus b cosine x equals the square root of a squared plus b squared. You can see this is important. Sine of x plus phi, where tangent of phi is b over a. You could recite this now. I've stated it enough times, and by now you should embrace it. So we're thinking this is really user-friendly. So here we have a equals 1, b equals 1, and then we're like, okay, well, that'll give us tangent phi. Nice numbers. So tangent phi is 1 over 1, which is 1, if and only if phi is our friend inverse tangent of 1, which is pi over 4. That comes up a lot in calculus. So when you're doing your integrals in calculus and you get this, you'll be happy that you took trig. And then, of course, a squared plus b squared is just 2. So now by the lemma, if and only if, what does this give us? We get the square root of 2 times sine. Of course, x has been replaced with theta. Theta plus pi over 4 equals 1. Now, when you look at this, and this is what I was talking about before, if you had to graph this, you'd have no issue with this. That'd be easy graph for you. I mean, you could do it. I mean, well, not the equation, but just this side here. That would be easy. So why is this good for equations? Well, this is one trig function. One trig function. And that's good. And it's first degree. So we're thinking we're in good shape here. So now let's just divide by root 2 so we get a nice number. So sine of theta plus pi over 4 equals 1 over root 2. Well, that's a friend from the unit circle. So theta plus pi over 4 equals inverse sine of 1 over root 2. Well, what is that? That's in the first quadrant between 0 and pi over 2, which again is pi over 4. So now you're thinking, okay, well, this is our argument, so to speak. So if we look at this, we see that the thetas absorb. And so we're thinking, okay, so this is theta equals 0. And then then we think, okay, well, wait a minute. For this equation here, because this is what we've reduced it to, let's put a box around this. This will work for any multiple of 2 pi. So 0 just plus 2 pi k. So this implies theta equals 2 pi k. Now, what's interesting about this is that when we look at this and we check the original, that's good too. Because what's tangent of 2 pi k? That's 0. Any multiple of 2 pi, the tangent is defined, that's 0. Plus 1, and secant of any multiple of 2 pi is 1. So 1 equals 1, cha-ching, okay? So even though we multiplied this equation by cosine, this did not turn out to be extraneous. So all of our solutions must contain this, okay? This is very important. Now we're thinking, okay, how do we finish this problem? Now, the thing is that for the new solution, so if we're going to have another solution in the upper arc that's congruent to this will imply now that we have alpha plus pi over 4 equals, well, now we apply Professor Ron's lemma to this, that'll be pi minus pi over 4 for the other solution. So again, we have to, in order to apply this, we have to look at this as being the argument to apply Professor Ron's lemma. So this is the argument here. And so now, what is this? This is alpha plus pi over 4 equals 3 pi over 4. And then if we subtract, we get 2 pi over 4, which is pi over 2. So subtracting gives us 2 pi over 4 reduced, we get pi over 2. And we're thinking, okay, well, is this any good? Well, that might be fine here. I mean, this works fine here, but notice it doesn't work here. Here, this is no problem. We expected this, but this is extraneous relative to the first equation. Tangent of pi over 2 is undefined. So observe, tangent of pi over 2 is undefined. That's a vertical asymptote. So we have to discard. So when you do this kind of technique, or if you squared things, which would have been much busier than what I've done here, you're still going to have to look for extraneous. So now we can say, well, we discard this. So this implies that the only case that gives us anything that works are all multiples of 2 pi, all integer multiples of 2 pi. And so if you stared at this, at the beginning, you're thinking, well, 0 works. Sine of 0 is, secant of 0 is 1. Tangent of 0 is 1, 1 equals 1. And then you're thinking, well, any multiple of 2 pi would work. So if you look at this long enough, this will start to make sense. So you're thinking our solution technique must provide this answer. And then you think to yourself, well, I don't see what else would work. I mean, I don't see anything else that would work. And your intuition is correct. But lots of times what I want my students to be able to do is to, with confidence, say, okay, well, I've used the technique and I used Professor Ron's lemma here to get the other solution, because I know the sine function is not 1-to-1 in 0 to 2 pi, especially in the upper arc. If you have a solution here, you have another solution here in the second quadrant. So this is what we were working on here. So this is the 3 pi over 4, which is the correspondent to the pi over 4 in the first quadrant. This is in the second quadrant. But then that would imply that alpha is pi over 2, which doesn't work here. So there probably won't be many instances where you will have this condition occurring, unless you either square or you multiply by some function that's variable. That's when you can actually introduce extraneous zeros. But we have no problem with that, ladies and gentlemen. That technique we use all the time. What's an identity? An equation that is true for all values of the variables for which it is defined. We don't care if there are a few problems here and there. Mathematics doesn't worry about that. But the main thing here is that this technique produces an equation that's easy. We can apply an identity and solve it easily, and then get rid of anything that doesn't work with the original equation. So hopefully, from what we've done in the trigonometry, you see how the unit circle fits together with the triangles. And now you see with the arithmetic of the unit circle, we develop a bunch of identities. We develop theorems about triangles, and then we see how they all mesh together, because basically solving equations drives all of them. Solving equations drives the inverse trig functions. It drives the triangle theorems. It drives solving equations, obviously. I mean, the thing is that someone discovered these sines and cosines and figured out that there's something good here when it comes to discussing motion and position in space, when it comes to looking at anything that has to do with orientation in our environment, just like being a surveyor. That's where you have to understand how to measure distances, measure angles. How do they combine to give you fruitful data? So hopefully what you're going to see from what we've done here is that we've given you a good foundation to study calculus. And what's left? Well, what's left are the conic sections. After the conic sections, we will work on some sequences, series, mathematical induction, and the binomial theorem. And then we'll be done. And so you'll be like, hasta la vista to this class, and then you can move on to Cal 1 and hit the ground running. So I appreciate your attendance today. Professor Ron will be glad for next week. It's supposed to get cooler again. I like that kind of cool weather. Now it seems like we're in springtime again, but I'm not complaining. I appreciate your attendance today, and good luck with your studying. If I don't see you at office hours or conference hours, I'll see you next week. Take care, everybody.